up of myself, Joey Lang, Jay Caldwell, Peter Epley, Pat Byerly, and our advisor, Dr. Bob Nagel. So when we began this project, all of us virtually had no experience with robotics and little experience with advanced circuitry. But as the semesters have gone on over the past 2 years, as the project has gotten more in-depth, we've each learned to specialize in a certain subsystem so that each person has found their own niche within the group. And these are listed under the roles and responsibilities of the team. So we have Peter, who is the team leader and lead programmer, Jed, who focused on sensor development, Joey worked on the circuitry, frame development, Pat and I both worked on the arena construction, Pat also worked on parts acquisition, and I worked on the drivetrain development. And so initially our design was based on the rules for the Trinity College Firefighting Home Robot Competition. And so that's where we got all of our constraints, customer needs, and mission statement from. But one of the big problems that we faced was that the competition rules from 2011 to 2012 changed significantly, and so we had to change our design based on this. So some of the changes include adding carpeting to the floor, ramps, variable door movements, and wall hangings that could affect different types of sensors. So we had to account for all of those in our design and change it based on that. And so as you can see here, those are some of our constraints and customer needs. We developed 11 total constraints and 13 customer needs based on these rules. And so the way the group determined it was that constraints are what must be done by the robot as set in the rules, and customer needs are what should be done based on how it would affect the score if we were to actually compete. And so, for example, one of the constraints is that obviously the robot must be autonomous, while a customer need is that it should be able to put out the flame using something other than air because it gives us more points. The next part of the design process that we focused on was developing a set of target specifications, which we developed 25 of them based on the components that we deemed critical to the completion of the robot. And so these were assigned a certain value or range, as well as an importance based on just low, medium, or high from the constraints and customer needs that we had generated. And so these target specifications were, as well as the constraints and customer needs, also took into account market research based on what parts were commercially available and within our budget, as well as researching previous designs and other similar designs, such as RC car motors and other small robotic devices. And after the target specifications were developed, we created a morph matrix and a functional diagram, which are basically just other ways of showing how each part interacts with the system as a whole. And those helped us to develop a schedule that we could stick to based on which parts needed to be completed first. And using all of these ideas, we were able to get a better idea of how the robot can be integrated as a whole, as well as working with the team and creating a working prototype. And now Jim will talk about the concept change.
Alright, so working on this project gave us two advantages before it's actually built. First, we knew our constraints that we could in competition. So that gave us, we knew our needs, we knew what the robot needed to function. So after knowing the functions, we decided on the functions. And we also used previous designs to see what they did, what worked in competition. So we had video evidence of the robots actually doing the winners, what they did. And through that, we found some things we really liked on those previous models. That was the change. Like we would like to just sort of design we found that robots that had torque motors could get caught in one circular base would turn and maneuver, and if they did hit walls, they would not get stopped. So viewing these, each of us made some concept designs. We have some that you can see up there. And we all got together, talked about the pros and cons of each of our designs, and came up with a single design that we really liked. And in the junior year, we had that. We put it into SolidWorks, drew it up. Even though we didn't know the exact sensors we were going to use, we could see how they would fit on there. We knew our wheel design. We're going to have 2 main motors and 2 swivel wheels so that the robot can turn circularly. And going into the next years, we actually started ordering parts and saw that our robot wasn't going to have enough space the way it was laid out right now because the parts were so much heavier and bigger than we thought. And because of the constraints from the design project, we couldn't make our base bigger because it had to fit in a certain box, but we did have space to go above. So we actually made a split level, as you can see in those next 2 pictures. We wanted to use those dollies to place the stand, and we thought it would be cheaper to use that. So we had wooden dollies, we had wooden setups for the sensors to bolt on. But as we started putting more pieces of parts on, especially the batteries, we found that it needed more structural support to help keep all that weight under control. So we actually added a metal frame on the bottom part, which bolted on. And instead of using the wooden, we used metal bolts. And those actually gave us more stability and gave us the option to raise or lower the top section. So that section also has our flame detectors, as you can see here. And one of the things we ran into is that during competition, the candle that has the flame will lower as it melts. So that gave us the advantage of being able to move that top to fit the height of the candle, giving our flame sensors a better reading. We also decided to go from a metal or round base to a polycarbonate, and that allowed us to see through the robot since we're using a lot of LEDs when we're testing. We can see the LEDs going on and off no matter where the robot was. Some other things, we had to change the 2-wheel swivel to the quarter because ramps were brought in with the change of rules. Putting 2 in the front gave us a different way to program it. We knew we had front and back to also get better going up ramps, so the 2 wheels would never lose power. And to speak up about all the technical details of these changes, Joe.
Initially, we thought we'd be able to use 1 microcontroller to control our robot. Then we realized that interrupts in our microcontroller were a necessity. What this meant was that we could only run 1 line of code at any given time. And that was a problem for the robot because we needed to monitor all of our sensors simultaneously, sending motor commands and measuring wheel displacement. Our solution to this was to use 2 microcontrollers that we had already acquired. And the upper microcontroller contains almost all the sensors, while the lower microcontroller contains motor commands and measuring wheel displacement. We created a full wire binary cable, communication cable, sent from the upper microcontroller tells the lower microcontroller what maneuvers need to be made based on the sensor readings. Each sensor produces an analog voltage. We tried to interface these sensors using an RC circuit in combination with a resistor or a transistor. And a built-in function, T-basic. This function charges a capacitor and measures the time that it takes for the capacitor to discharge, producing a digitized value based on the time that it takes to discharge. We prototyped this circuit seen here on the table, and it worked, but it created delays in our programming because of the time necessary to charge and discharge the capacitor, which created delays in making our robot move around the arena. In order to fix this problem, we decided instead to use an analog 12-bit analog to digital converter. Our microcontroller didn't have an analog to digital converter built in, so we had to buy an integrated circuit. This analog to digital converter uses a clock signal along with serial interface to transmit the data collected from each sensor to the microcontroller. We also plan to build a motor driver from transistors, but the schematic that we used in order to build the motor driver seen here didn't work because of the difference in voltage that the microcontroller could produce and the voltage that was necessary to drive the drive motors. Instead, we bought 2 integrated circuit motor drivers that were pre-built. These were compact and gave us a cleaner interface, as you see here. They also added a dedicated standby pin and pulse width modulation pin, which made the interface with our lower microcontroller more convenient because we could have dedicated pins to each of those. Now Peter's going to talk to you all about the testing and programming that went into the robot.
For the testing and refinement phase of our project, this is where we spent most of our time, especially the last couple of weeks. As we got each component in, we ran each one through a trial with just a single microcontroller to kind of get an idea of the range of sensors, the range that they could interpret and how that would work with our program. As we tested each sensor, we then also kind of discovered the different ranges where they were the most accurate. With the graph that you see in the bottom left corner here, that shows a test of our IR sensors, in which it shows the usable range is somewhere between anywhere greater than 6 centimeters. Anywhere within that range, there's kind of a copy of what's kind of the same readings that would occur as if it was further. So in order to kind of avoid that, we went ahead and mounted the sensors themselves on the frame of the robot so that the range where they were inconsistent, it would not actually fall into that range. The robot would be able to stop itself before it got here. In order to test the robot altogether, we also constructed a maze, which you can see in the top picture there. And we have that later that we can show for anyone that wants to see it for presentations. But in that maze itself was very similar to what we would have seen going up to Trinity, Connecticut. And the robot itself would have to navigate through. We developed several different combinations with the sensors, but depending on the readings they got, they would know where in the maze it was and how it would need to react. The IR sensors, which are the top 3 here, the one, not the 3 on the metal, on the aluminum mounted there, but 3 around, and that's point 2. Those worked in combination with the microcontroller to sense if there was something within the range that would know that it needed to make a turn or it needed to veer around in order to keep itself straight and keep itself from running into any obstacles. When the robot itself actually enters the room, we were able to determine this by an empty reading on the front and the right sensor. So the robot would know to move forward and make a right turn in. Once the robot entered the room, it would cross over a white line which would trigger the QTI sensor and activate our flame surge code, which would also activate the top 3 sensors, our DFR flame sensors. Going through that, there were several times when we had to go through, kind of test the components, see what they would do. And we actually ran into several problems, especially with our microcontrollers and just some of our individual parts. One of the issues we ran into, and why you see a lot of the tape around the robot, is that we had a lot of loose wires, and as we would connect them, if one popped loose or if we forgot to connect one at one point, it could actually ground or short out part of our robot. We had this happen with one of our microcontrollers when we had to later replace. This was actually fortunate because it allowed us to solve one of the other issues we had with our microcontroller, which was the processing speed. As Joey was talking about earlier, we can only run through codes one line at a time. So in order for the robot to do something else, it would have to finish a line of code. So it wasn't able to really run simultaneously commands. So really speed became our issue. Communicating between the 2 microcontrollers was also an issue that we were able to resolve using the binary signaling just on and off methods. Another thing we ran into is a couple of faulty components. Our extinguisher, just this last Wednesday while we were testing it, suffered a severe malfunction that caused it to fracture the interior of the component and prevent the extinguisher system from working any further, just due to the high compressed CO2 and kind of causing flash freeze. We also had an issue with some of our optical sensors, which do our wheel counts for the robot. And using the microcontroller, it relies kind of on those counts in order to see where it is, how far it's going, and to execute the turns properly. When one of the sensors malfunctioned, the robot would just continue to run the command as it was not able to count the number of counts. So we had to kind of tweak a little bit, a couple of things in order to secure the sensors better and help keep their communication up. The final thing is also our back wheel that is on a swivel. We originally had a caster wheel there, but due to the weight kind of the batteries and everything on the backside of the robot, it would cause the wheel to frequently lock up and also would just kind of get into the ball bearings. So we later had to go ahead and replace that with a omnidirectional wheel so that the robot would be able to maneuver a little bit better and not get caught up with into walls or not be able to maneuver properly. And now Pat will talk about sustainability.
Our program really preaches sustainable design. So as a result, we tried as much as we could to implement that wherever we could. There are obviously budget constraints, time constraints, and limited knowledge base that prevented us from doing everything that we wanted. But we were, from an economic point of view, we were able to stay within our budget by using parts that were slightly less effective but a lot cheaper. For example, the flame sensors in the front, the three that they're pointing out, those are all $3 a piece as opposed to using an $80 sensor that do roughly the same thing. Other than that, our most expensive component was $60. The other cheap aspect of it is that the extinguisher canisters are only $267 a piece to replace, which is not much at all. From an environmental standpoint of view, it's modular, so we're able to disassemble it easily, which helps us to, if you want to dispose of it properly, that makes that a lot easier. And also, if you want to reuse any parts, we're able to do that as well. All our robot mountings were made from scrap metal and plastic that were lying around the shop. From a social point of view, a scaled-up version of this could be used for hazardous situations. In addition to that, it requires little human interaction. It's very user-friendly. You basically just push the button and it does everything else. From a technical point of view, like I said before, it's modular, so if someone wanted to disassemble it, maybe redesign it, or see how it works, it'd be very easy to do that. The robot was built with little to no knowledge prior to the project, so it doesn't take a whole lot of teaching to be able to do this in another setting. It has custom circuitry that's not too complicated and would be easily recreated using publicly available diagrams. Batteries and the extinguishers, when they do run out, they're not expensive and they're very easy to replace on there. That's about it. So we'd like to thank you guys for your time and entertain any possible questions that you might have.
The 4 binary lines that run between the two controllers that you have, what signals do those carry?
It's a digital on-off signal, and depending on the series of ons and offs, that produces the binary number, which lists what motor needs to be taken.
So which is the master and which is the slave?
So the upper microcontroller is the master, and it designates what the lower microcontroller needs to do. The lower microcontroller just has a set commands. It has a switching function based on whichever number is transmitted to the communication table.
What microcontroller could you have purchased to allow you to use it? Would that be possible?
It's possible. Arduino makes a microcontroller with 2 interrupts. The interrupts allow you to run multiple lines of code at the same time. It allows like a background function to run while simultaneously going to another function. So you would probably use Arduino.
And that would take care of it.
Use decimals.
We had to do a lot of math to get the program to understand what the numbers are.
And then also Arduino has a pretty big community. They have a website, an entire forum, pre-programmed code, not programmed, but pre-written codes.
Scaled up model of these version of these. What are the extra constraints that you have? You say it can be.
You'd have to definitely scale up the extinguishing power a lot. The big constraints is lot easier in a place like that. You'd probably be able to use heat a lot more. The candle gives off little or no heat, so that wasn't really an option for our sensors. And if you had a big flame, it could be easily fired. Ours have to be very accurate to dial in that extinguish.
The flame sensor works like, how does it work?
Basically, we have 3 sensors, so we'll see what each sensor sees and try to focus in on the middle sensor. So the robot will turn and center itself towards the flame, trying to keep centering itself.
So in there is what?
The frame sensors, they're shielded with this speed, so that only the frequency of light that comes off of the candles with the sensor. So they all because of the frequency, they're not getting confused with the rest of the light that we also calibrated them based upon those lights, like when we were running our tests, we were testing them down in a black environment, but in order to bring it to another environment, we were the ones that again have to run those tests in order to compensate for the natural light or the artificial light that's generated.
There are a lot better sensors to sense flame that can do it a lot more accurately. These are just shrouded photodiodes. It's a really simple setup right like this, but those are triggered right for that flame direction. So we actually had to work on the circuitry of that to get them to get the range we wanted, but they're very good at sensing just that amount of it.
So what would be your extra consideration as far as the material, the robot itself, the real life
I was going to say everything would just generally have to be scaled up. I mean, it probably a more real life environment. A lot of these components would probably not be able to stand the incredible heat that would be in an actual large fire. Also, the power sources that we're using, the batteries themselves are very small. They're only powering these components. In order to have the big components, we definitely need a bigger battery, or else the robot would just kind of shut off and then try to navigate around the flame. The CO2 canister like we were using, that once again is very small. I think it was only 15 grams of CO2 compressed at 120 psi. So that would definitely not be enough to put out a large fire. So just all the components would just generally need to be scaled.
And then there are additional factors like debris,